Okay, so tonight we are going to talk about section 7.3 in the textbook on the topic of differential equations. And we are really going to look at the tip of the iceberg. This doesn't really do justice by the main topic. This topic is really covered extensively in Calculus 4. So that Calculus 4, whether it's AMS 361 or MAT 303, is a full undergraduate course in this topic. So we're abandoning our story of series and we are looking at this topic called differential equations, which is really the basis for Calculus 4. It is probably the most applicable topic in all of calculus as well, and I'll show you a couple of applications tonight. But you might say, why are we doing it here? It's pretty standard in the United States to do one lecture or really one mini unit on this. So a couple of weeks or in a once a week class like this, one lecture. So you just get the gist of this in case you don't get on to Calc 4. That way you get to see a really important topic in calculus. But if you want to see it in much greater depth, you take Calculus 4. So with that being said, let me show you an example of a differential equation. So our first example tonight, we will have a differential equation, dy dx is equal to x cubed. So this is an example of what we call a first order differential equation. So it's called a first order differential equation, and we can abbreviate that DE. So this is a first order differential equation. It's called first order because it's the first derivative, not a second or higher derivative. So this is considered the first order differential equation, dy dx is equal to x cubed. So we call this a differential equation. And of course, with equations, we want to solve. So we're looking to solve this differential equation. And basically, we begin by saying, find what we call the general solution. At first glance, this is actually pretty easy. So when I ask you for the general solution, it's basically just asking you what y is equal to. So I bet most of you even know the solution already. So what is the general solution? If the derivative is x cubed, what would your general solution be?
Is it 1/4 x to the fourth?
Exactly. All you're going to do is find the antiderivative, which is x to the fourth over 4. And then you're going to do plus c for the infinitely many solutions. So at first glance, this is just integration, but without using the integral symbol. So dy dx is equal to x squared. The general solution is y equals x to the fourth over 4 plus c. So that's our solution here. So again, all I did was give you an equation, a differential equation, and you're finding the antiderivative. Give the solution. Okay. So with that being said, suppose I give you dy dx is equal to, let's say, cosine x. And I also tell you that y of 0 is equal to, let's say I tell you y of 0 is equal to 2. So in this case, I give you what we call an initial condition. So we have a differential equation again. It's dy dx equal to cosine x. And this time I give you an initial condition. When I give you an initial condition, I ask you sometimes for a particular solution. So some jargon here. A particular solution is what I'm asking you for in this case. And that means you can actually find the c because of the initial condition. So once again, solving the differential equation, if dy dx is equal to cosine x, this is pretty easy. What's the solution here?
Sine x.
Right, so it's actually sine x plus c to start. But because I gave you an initial condition, you can actually plug in and find out what c is. So y of 0 equals 2 is synonymous with 2 equals sine 0 plus c. But since sine of 0 is 0, we actually find out that c is 2. Writing our particular solution, we get y equals sine x plus 2. So this is our particular solution right here. So with that being said, let me give you just a quick practice question on the simple version of what we're doing right now. So suppose I tell you that dy dx is equal to e to the negative x, and suppose I tell you that y of 0 is equal to 4. So I would be asking you here for a particular solution. So why don't you just take about 2 minutes here and see if you can find the particular solution. Keep in mind, last time I told you to memorize what an antiderivative of e to the negative x would be, so you could actually bypass using u substitution. So take a moment here. The derivative is e to the negative x, and y of 0 is equal to 4. Find the particular solution. So in this case, if you're looking for the antiderivative, hopefully you remember it's negative e to the negative x plus c. The plus c would be a general solution. However, y of 0 is equal to 4. So 4 equals negative e to the negative 0 plus c. In this case, 4 equals, well, e to the 0, so this is negative 1 plus c. So it turns out that c happens to be 5 here. So right away, we can give ourselves the particular solution of negative e to the negative x plus 5. So that would be our particular solution. And right now, this is nothing more than just basic integration. I'm going somewhere with this pretty big tonight. And in number 4, actually, I'm going to do a real-life example based on the simple cases, and then we'll move on to something a little loftier. Questions here? Okay. So number 4, let me actually do this in pieces. Suppose I do dy dt. Let's bring in our friend t. Suppose I tell you dy dt is equal to, let's say, and I think I'm going to go somewhere pretty good with this. Let me go with negative 9.8. And I'll let y of 0, I will let that be a constant that I will deliberately call, in anticipation of what is to come, v naught. So let me begin here with dy dt is equal to negative 9.8, and I'll give you an initial condition of y of 0 is equal to v naught. So find the particular solutions. Everybody participate in this, because I'm going somewhere pretty nice with this. Just take a moment, find the particular solution, and we'll see what's happening. So if you try to solve this, it's pretty easy, because this is a constant. So the antiderivative is the constant, negative 9.8 t, and of course you get the plus c. Now, what happens here is if you plug in y of 0 is equal to v naught, you wind up getting v sub 0 is equal to negative 9.8 times 0 plus c, giving us, of course, c is equal to v naught. So y is equal to negative 9.8 t plus v sub 0. Okay, so there's the solution, but I'm going somewhere with this on purpose. So just take that for a solution, and then I'm going to do something in number 5 with the answer on purpose. So in number 5, let's pretend for a moment that dy dt is equal to the solution that I just got, negative 9.8 t plus v naught. And this time, I'll give you another initial condition, and I think I'll say y of 0 is equal to, I don't know, I'll call it s naught. So this is where something pretty miraculous happens, and I think some of you can probably see already something from your past. So dy dt is equal to negative 9.8t plus v naught, and y of 0 is equal to s naught. So what I'd like you to do right now is find the particular solution. And I claim when you're done with this, you will have derived something from your past. So find the particular solution. This example definitely deserves the lights. Okay, so a little bit exciting here. If you want to find the solution, you need the antiderivative. So it's negative 9.8 t squared divided by 2 plus v naught t plus the constant c. So in this particular case, what I'll wind up doing here, what I'm going to wind up doing is I'll just plug in s sub 0 is equal to negative 9.8 times 0 squared over 2 plus v naught times 0 plus c. That gives us c is equal to s naught. So the solution is rather exciting here. Negative 4.9 t squared plus v naught t plus s naught. Surprise. I just derived what famous formula from your past? What is it?
Kinematics equation, physics.
Yeah, absolutely. It's really projectile motion. This is the projectile motion. I did a specific version, if you care, of 1/2 at squared plus vit plus, I don't know what they would call this constant, maybe SI. But this is where it comes from. I can't stress enough that the physics formulas on the reference table from high school did not just magically appear. It starts with acceleration. It starts with acceleration, and then it backs up to velocity, and then it backs up to position. That's how life goes. That's how things arise. It's not as if someone had the position formula. Differentiation is not really what happens in real life. It's integration or anti-differentiation that happens. Someone knows a fact about a rate and they work backwards. So we really start with the fact that the planet Earth has the gravitational constant negative 9.81 meters per second squared. That's the acceleration. And then we back it up. Of course, this particular formula is really for things that happen in a vacuum. This is like the dropping the ball or throwing it from a roof. But again, there's no wind resistance. So it's kind of a little contrived, but it is the famous formula that you see from physics in high school. So this is just one classic example, and this is not even with solving sophisticated differential equations, but we instantaneously derive a famous physics formula right off the bat. Any questions here? Okay. So really the topic gets started now, because this is where things get interesting. This is where the topic really starts. Okay. So I want you to tell me what's different about this differential equation in contrast to the other 5 that I've given you so far.
The derivative is in terms of y.
Yeah, this is absolutely essential that you notice this. This is very good. The derivative is in terms of the dependent variable, not the independent variable. So in some ways, it's kind of like reverse implicit differentiation from Calc 1. But implicit differentiation in Calc 1 was very abstract. Going the other way is actually very applicable and concrete in some way in Calc 2 right now. But dy dx is equal to y, and we want the general solution. So here's my interesting question to start. Literally, this says the derivative of a function is the function itself. So if you actually try to write out this differential equation literally, this is the rate of change of y is the function y itself.
Like e to the x?
Right, like maybe e to the x. So that's going to be my question for you. You said e to the x. I couldn't have asked for a better first response. Like maybe e to the x. So I'm okay with e to the x because e to the x is definitely a solution. Definitely. Derivative of e to the x is itself. Here's my question. Find the general solution. You found one of infinitely many solutions. What's the rest of them?
Plus c.
Ah. You are absolutely wrong. But I led you into that. E to the x plus c. Wrong. But I totally, that was entrapment on my part. Definitely entrapment. You want to say e to the x plus c, but take a look at why it's wrong. Derivative of e to the x plus c is e to the x, not itself. That was entrapment on my part. I led you right into that.
Like the natural log of y is equal to x.
Maybe. I mean, that's interesting. But then we'd have to figure out what that is in terms of y. So we have an interesting little game to play here. Finding all the possibilities here. You actually missed another easy solution. You missed an easier solution, even easier than e to the x. You missed what we call the trivial solution. There's another function whose derivative is itself, and it's easier than even e to the x. You could have learned it before you even learned e to the x. Anybody know? There's another easier solution. This is one solution. There's another one.
0.
dy dx.
Yeah, 0. Y equals 0 is another of the infinitely many solutions. So the question is, how do you get the infinitely many solutions? So this is something we're going to learn tonight, and this is probably the key concept. The differential equations we're going to study in this course are called separable differential equations. So there's many different types of differential equations. We're going to learn about separable differential equations. And in order to solve something like this, separable means the y's and the x's can algebraically can algebraically be separated. So we're going to learn a process now that we're going to utilize for the rest of the lecture. So dy dx equal to y. I claim that the rest of the differential equations we're going to look at tonight are called separable. And it means that you can isolate y's from x's. So with dy dx is equal to y, I'm going to go through a process with you in order to get the solution here. So the first step that we're going to use, and I'm going to put this in quotes because most math professors would crucify me for saying it because it's not really called this, but I'm going to put it in quotes. Cross multiply. So thinking of the derivative as the change in y over the change in x because it's slow, take a moment to quote unquote cross multiply. Now, technically, it's not cross multiplication. It's the theory of differentials. These are differentials. You can prove if you took a very rigorous Calc 1 class, you can prove that dy is equal to y dx. But in essence, it's kind of treating these as separate quantities. Problem in Calc 1 is that you often think of dy dx as one individual quantity representing the derivative. But for all intents and purposes, this mechanism works here. So, quote unquote, cross multiply dy is equal to y dx.
Professor,
Yes.
just out of interest, what's the difference between dx over dy and dy over dx? Just to clarify.
Well, if it's dx over dy, that's just the change in x over the change in y. But that really has no basis for calculus because that's not the slope. The slope was really defined as the change in y over the change in x. So you're very rarely going to see dx over dy.
Oh, that makes more sense. Thank you.
Sure. So you get dy is equal to y dx. And if we're trying to have steps here, if you will, you're going to divide in order to separate variables. So what I'll do here is I'll divide by y on both sides. So all I did in step 2 was divide. So what happens here now is I have 1 over y dy is equal to dx. So things are pretty good here now. Things are pretty good because you have y's on one side and x's on the other. So it is deliberately set up for you to integrate both sides. So step 3 in this process is to just take the integral on both sides. And it's set up perfectly because the differentials dy and dx are right here. So what's going to happen now in the next step is you're going to have integral of 1 over y dy is equal to the integral of, and of course there's an imaginary 1 here, integral of 1 dx. So you've kind of done everything you need to do to set this up, and now the rest is just go from there. So let's go one step at a time here. On the left side, we need the antiderivative of 1 over y. So the antiderivative of 1 over y is ln of the absolute value of y. Then we go to the other side, and the antiderivative of 1 is just x. And let me just tell you that the customary conventional thing to do is to put the plus c on the x side. Don't put it on the y side. If you want the reason behind it, it's silly to put the plus c on both sides. So let me just show you why you never do that. ln of absolute value of y plus c equals x plus c. That's silly because you're not allowed to necessarily say the c's are the same, and then they would cancel. So then if you're like, okay, let me be more appropriate and put plus c1 on one side and then c2 on the other side, but that's so silly because if you subtract c1 from c2, then you get ln of absolute value of y is equal to x plus c2 minus c1, which is just some other constant. So all of this is what I call silly. So all we do instead is just opt to put the plus c on the x side. So rule of thumb, only put the plus c on the x side. So we have ln of absolute value of y on the left side, x plus c on the right side. That's where we're at with this. Okay, so we're pretty much done, but we want to solve for y, of course. And this goes back to pre-calculus. If you want to solve for y here, and here comes a nice word I love, we exponentiate, which is just put e raised to both here. E raised to both, and e to the ln of the absolute value of y is just absolute value of y. And this is fine the way it is, but it behooves you to use the laws of exponents and to factor it in this form, e to the c, e to the x. So all I did here was I raised e to both sides so that I could appropriately solve for y. But right now I get absolute value of y. And then over here, this is perfectly fine the way it is, but it's kind of fun to factor it to get a better version of it. And then we get absolute value of y is equal to e to the c, e to the x. But if we want to solve for y to get rid of the absolute value, it's plus or minus e to the c, e to the x. But here comes the best part. Plus or minus e to the c is just some constant that I'll call, I think, a, just some general constant. And surprise, surprise, you have found the general solution. And now you're going to scratch your head and say, oh, darn, I should have known that anyway. Y equals a to the x, a e to the x is the solution. You knew this all along because, and I'll go back to that slide in a minute, if you have y equals 5 e to the x, everyone, what's the derivative of 5 e to the x?
Five e to
Itself. If you have y equals negative 9 e to the x, what's the derivative? Of course, it's itself. And if dy dx is equal to e to the x, that's just, rather I should say, if y is e to the x, of course we know that's just a special case. Dy dx is equal to e to the x. And 0, of course, is just 0 e to the x, which of course is itself. You have encapsulated all of the solutions here in the form y equal a e to the x. This is called a family of solutions. It is indeed the general solution.
Professor,
Yes.
I was looking this up, and it said online that it was like a function that's a derivative of itself, like e to the x is like useful things like compound interest, but I don't really get why.
Oh, don't worry. I'm going to show you tonight. Don't worry. That's coming. I promise. That's a big deal for tonight. So that is definitely coming your way. Perhaps the highlight of the lecture. Okay. Any other questions just about the process here so far?
Could you go through the steps again on the slides?
Yes, sure. So the steps are, number one is really multiply rather. Step 2 is divide. And step 3 is integrate on both sides.
Thank you.
Right, and then you're going to just take it from there the way we did in the problem.
Professor,
Yeah.
I was going to ask, isn't e like its own constant, like a number? Like I'm
Well,
confused.
Yeah, well, E itself, by itself, is approximately 2.718. But this is the function e to the x. So it is the constant 2.718 to the x. But E itself, the number E by itself, is approximately 2.718.
Okay.
Okay, so let's try. I want to try another one with this before we get into anything with word problems or anything else. So let's. All right, we are up to number 7. Okay, so number 7. Let's try just for a moment here. One more like this. dy dx is equal to y squared. Okay. Find the general solution. There won't be any logs in this problem, but the process is pretty similar. So I want you to try this. Just keep in mind there's no logs or e in this problem. We'll come back to that soon. But just to keep us honest with the process, this time you're finding a derivative. You're finding functions whose derivative is itself squared. If you decided to sit around and think about this one, you'd be crazy because it was hard enough with even the e to the x. It's going to be near impossible to sit around and just kind of guess and check functions whose derivative is itself squared. That would be borderline insanity. So why don't you take a moment here and see if you can follow the process of separating variables to see if you can get the solution. Okay, so let's see what happened here. If we do that cross multiplication thing, we get dy is equal to y squared dx. And then if we do the division, we wind up getting 1 over y squared dy. And we have the dx on the other side. So then we do the integral on both sides. a little imaginary 1 here. Don't fall for the trap. This is not a natural log question. It's better for you to write this as the integral of y to the negative second dy is equal to the integral of 1 dx. So this is not a natural log problem. So over here, this is a power rule question. You add 1 and divide by the new power. And on the other side, no plus c on the y side as per the last example. And over here, we wind up getting x plus c. So this is pretty good. I think I'll turn this into negative 1 over y equals x plus c. And this then becomes a solving for y question here. So if we want to solve for y here, I would divide both sides by negative 1. And then, an old trick, just take the reciprocal of both sides.
Simple.
Oh, we lost it. Okay, okay, so where did I end off? Can you see this here, or you can't see anything anymore?
30.
Hello.
That's it.
Is negative 1 over y is equal to x plus c.
Okay, so negative 1 over y equals x plus c. You can see that. So I'll be right back as we can do this in 40. I calculate. It looks like it's 38-minute segments. Okay, so I'll be right back. Bye. So the last thing that you saw was what? No, tell me what you had last.
Negative 1 over y is equal to x plus c.
Okay, perfect. So we want to solve for c then. So the trick then is to just divide everything by negative 1. This is easy algebra. And then an old trick to solve for y is just do the reciprocal of both sides. That's an algebraic correct maneuver here. And then we wind up getting this. And there it is. That's your general solution. It's a rational function, 1 over negative x minus c. So that's your solution here. No logs in this problem whatsoever. Any questions about this?
Yes, I have a question.
Go ahead.
So I flipped it first, then I divided by negative 1. So
You have this instead, right? You have this?
yeah.
Same thing. They're equivalent. Perfect. No problem. Anybody else? Okay, so we're going to do something similar. What am I up to? Number 7?
You're
Yes?
up to 8.
You're up to 8.
The number 8. Okay. So number 8. So dy dx is equal to 3 square root of y. But this time, and y of, I want to do y of 4 is equal to 1. Okay. So I just have, this is very similar to the last few we did, but notice I have an initial condition. This is the first time I have an initial condition when there is a separable differential equation when I use the process. The only thing I want to tell you in this problem, and this is my rule of thumb, it's not definitely a mandate, but I want to just tell you what I always say. Find C when it first comes about. Solve for y later. So all I'm going to tell you is number 8 is just like number 7, except when you get the plus c, find the plus c with the initial condition before you solve for y. So my rule of thumb is to get c before y. So find c value, which can be obtained because as an initial condition, there's a point. Find c before you find y. And then this question is rather similar to number 7. So I'd like you to try it, but remember to use my rule of thumb here. Find the c first, and then get the y. Don't solve for y and get the c. While you quote-unquote legally can, it's not my pedagogical advice to you. So let's everybody give this a shot. Yeah, go ahead.
Is that the cube root of y, or is that 3 times?
Funny you say that. I didn't mean for it to be that. It's 3 times the square root of y. I'm glad you correct. It was correct, but let's just make sure that it looks right. Thanks for saying that. So this is the 3 times the square root of y. It is not meant to be the cube root of y. It's meant to be 3 times root y, square root of y. Okay, so go ahead, try. dy dx is equal to 3 square root of y, and the initial condition is y of 4 is equal to 1. So see what you can do with this. Okay, so here we go. So we're going to do our normal cross here. So we get 3 root y dx is equal to dy. And a couple of things here. So there were a couple of ways to proceed, but I'm going to leave the 3 with the dx. It's probably better. You can do it both ways, but it'll make life easier. Divide by square root of y. So that's 1 over root y dy. It's probably better than to say 3 dx is equal to y to the negative a half dy. Then we can integrate both sides. So a couple of things here. While you could bring the 3 to the other side, I think it's easier to leave it in general with the dx. So that's kind of another little piece of advice I have for you. So now we have the integral of 3 dx is equal to the integral of y to the negative 1/2 dy. So on the left side, the antiderivative is just 3x plus c. And then the antiderivative here, I'll just move to the side for a moment. Just add 1. So negative a half plus 1 is to the 1/2. Divide by a half, which is multiplying by 2. So there's your antiderivative. It's just 2y to the 1/2 power. Now, if you were remembering what I said, c just came to fruition. So y of 4 is equal to 1. So it behooves you to find c now. So what I would do is just 3 times 4 plus c is equal to 2 times 1 raised to the 1/2 power. Get c now. So this becomes 12 plus c equals, order of operations, this comes out to be 2. If you solve for c, c comes out to be negative 10. So we did this to get rid of c, or to get c right now. This becomes 3x minus 10 equals 2y to the 1/2 power. So just going back for a moment, all I did was solve for c by plugging in the initial condition y of 4 is equal to 1 here. This allowed me to get c. Then I'm here, and now I can solve for y. So to solve for y, I'll just divide both sides by 2. So I get 3x minus 10 over 2 equals to, well, y to the 1/2 is square root of y. Solving for y is easy. Just square both sides. So you wind up getting the quadratic, 3x minus 10 over 2, the quantity squared. That is the particular solution. Go ahead, question.
Professor, I did exactly what you did, but I got a different c value and I got the right answer because I just moved the 1/3 in front of the integral, like 1 over rad y.
Yeah, you can do that. So if you left the 1/3 there, you could also get the right answer. So bringing the 1/3 on the other side works just
But
as
I got
well.
a different c.
At the end, you got a different c.
Yeah, I got negative 10 over 3 because the left side was like 2 over 3 rad
So
y.
this did not come about the right
No,
way.
I got that answer, but like a different c value.
If you got this right, and the C is different because of what you have, that's fine. If it's because of the way it is in the problem, this is fine as long as you wind up with this.
So it's okay to have like different C's like in the middle of the problem as long as you get to the right time.
Your C is based on what you have in the integration, so it is okay as long as you can wind up with the exact same particular solution at the end. Anybody else so far? All right, now for the highlight of the lecture, and then we'll come back to some more abstract ideas. But now for the highlight of the lecture, and I want to just talk to you about how big of an idea this is. We heard a question before about, I heard about compound interest and all this other stuff, and this is really where it's at here. So first of all, I want to just, in number 9 here, I want to talk about some real life stuff for a minute. So I want to just, I'm going to put my stylus down, and I just want to have a little talk with everybody about a possible real life scenario. Okay. So I think my situation is going to be people in a city. Let's just talk about this. People in an urban setting. Picture it. People in a city. Okay. What generally happens with people in a city? Generally.
Disease.
Say it again. Disease. Okay, true. Disease.
Population grows exponentially.
Yeah, so even despite the disease, the population somehow tends to grow. I think I read once, like for every one person that dies, 3 people are being born. Okay, and you said the population grows exponentially, which is a colloquial thing that we say all the time now when something grows rapidly. But it actually comes from or stems from what we're about to discuss here. This is the premise. I'll pick my pen up again here because this is the premise from social scientists. When you go into an urban setting like a city, or maybe it's not even a city, maybe you're talking about a bacteria colony or like a farm of jackrabbits or something. But the premise is the following. The faster the population grows, the more people, bacteria, jackrabbits there are. This is the premise that I'm going with. So you're a social scientist, and you have to make a statement about the rate. The faster the population grows, the more people there are. Can we all agree that that's a reasonable hypothesis in a city? It's reasonable.
Is that also analogous to if there's more time and there's more interest?
Well, that's a little bit different, but you're on the right track. So I know you're kind of focusing on this interest thing, so just bear with me a little bit longer. So you can say lots of things, but right now it's just the faster the population grows, the more people there are. I guess you could make the following assumption. The more money there is, the faster the money grows, or the faster the money grows, the more money you have. So that's kind of the analogous statement. So the faster the population grows, the more people there are. We have another way of saying this in math. So another way of saying this. Another way of saying this. The other way of saying this is the rate of change of the population is directly proportional to the population. So a more mathematical way of saying this, and you've heard this in the past, 2 quantities are directly proportional. If you forgot about directly proportional, you may have remembered from high school something called direct variation. So like direct variation is really what we call directly proportional. This is like the answer to every like biology or economics question. So it's like two things that are growing in a direct relationship with one another. So this is y equal kx. Y equal kx is when y and x are directly proportional to each other. This time, I'm just saying the rate of change of the population is directly proportional to the population. So what this really means is that the derivative of the population, I'm going to actually use t instead. The rate of change of the population is directly proportional to the population itself. Of course, k is positive. So let me just say that I'm going to go back for a moment. This premise, the faster the population grows, the more people there are, is synonymous with the rate of change of the population is directly proportional to the population. Same thing. The mathematical equation for that, is this: rate of change, where y is population. You can say y is population. The rate of change with respect to time of the population is directly proportional to the population. So dy dt is equal to ky. That equation is literally the equation for the rate of change of the population is directly proportional to the population, which is synonymous with the faster the population grows, the more people there are. So all I did was write a mathematical equation for the faster the population grows, the more people there are. That mathematical equation is dy dt is equal to ky. K is bigger than 0. And of course, if you have an equation with a derivative, it is in fact a differential equation.
Professor?
Yes.
You said they're proportional, not that they're equal, so I'm a little confused.
Right. Okay, so proportional, just so you know this. So if y is proportional to x, that means y equals kx, because you start from here and you go there. So for example, if k were happening to be 2, like 2x, like if you pick an x value like 5, y is 10. If you pick an x value like 7, y is 14. But if you make a proportion 5 to 10 is equal to 7 to 14, voila, it's indeed a true proportion. That's where this comes from. So this is just kind of back from, and it's kind of taught in kind of a little bit of a shoddy way, but nevertheless, I think math educators have made some improvement, but it seems to lose its connection to this, which is why I make such a pretty big deal of it now. So dy dt is equal to ky. That's the equation that means the derivative is directly proportional to the amount present. So this differential equation, dy dt, is equal to ky, means the rate of change is directly proportional to the amount present. And I'd like to give an initial condition. I'm going to call y of 0 equal to p. So I'm going to have an initial population, if you will. I don't want to say it's a billion or a million. I'll just say it's p so that I don't tip my hand. So I'll give an initial population here, and I'll just call it p. So before your very eyes, you have a differential equation with an initial condition. The differential equation dy dt is equal to ky literally means the rate of change is directly proportional to the amount present, which colloquially means the more people there are, the faster the population grows, and vice versa. So here's the exciting part. Because this is a differential equation with an initial condition, you can find a particular solution. And I'm going to ask you to do exactly that right now. dy dt is equal to ky and y of 0 is equal to p. I am asking everyone to solve this differential equation. It's very similar to what we just did in the last example. Because it's y to the first power, logs will be used again. So take a moment. Absolute value actually can be eliminated in this problem. there is no absolute value because population can't be negative. So whenever an absolute value comes about, just ignore it, or throw it out rather, because it's population, people who can't be negative. So I'm going to give you this question, and the result is astounding. So take a moment now, find the particular solution. We have reduced the real life scenario to a differential equation with a generic initial condition.
So is this just sort of a simplified version of logistics? Like, would we be getting into that at all?
Well, so I'll talk about the logistic. So let's solve this differential equation, and then I'm going to talk about the logistic model in just a moment, which is another differential equation that can be solved, but it's a little bit harder. So let's just go with this, and then I will talk about the logistic differential equation.
Professor,
Yes.
I understand this, but just out of interest, I thought technically k is the slope, so shouldn't that just be equal to dy dt?
Well, right. So, okay. So if dy dt was equal to k, the slope, k would be a constant. That would be the slope being constant, so the function would be linear. The derivative is changing at every point. So as y gets bigger, the rate of change gets bigger. You don't want it to be just k, because then it would be a linear function, and population does not grow linearly.
Oh, okay.
So, yeah, so dy dt is, if it was just k, that would be the slope of a line. The problem in calculus is that the slopes are changing. Calculus is about the rates of change changing. So it's not just k, it's k times something else. All right, so take a few moments here because the result is spectacular. So I'll just take another minute or two, see what happens.
Bieber?
Yeah.
Yeah, I know it's kind of a dumb question, but like, since this is Calc 3, like, is it going to be on the final, or?
No, this isn't Calc 3. So this is actually the beginning of Calc 4, but it's traditional to do this topic in all Calc 2s across the country. So yes, this week's topic and next week's topic, although they are separate from the story, will be on the final. So yes, this will be on the final exam. Not a stupid question.
Oh, I'm sorry. I confused it with Calc 3. Like, I was...
No, so interestingly enough, this week is a topic that is traditionally done at the beginning of Calc 4, and next week I look at a topic that has a little bit to do with Calc 3. But they are both traditional in Calc 2 and are appropriate for the final exam.
Professor?
Yes?
Just to be clear, k isn't a constant?
K is a constant. But you can't
How does it change, though?
Because it's a constant times y. You keep asking me if the derivative is just a constant, period, but it's a constant times the variable y. K is a constant.
Okay.
But yeah. All right, take one more minute and then we'll go over it. Okay, so if dy dt is equal to ky, y of 0 is equal to p. If we cross, we get ky dt is equal to ky. Ky, actually, that's a mistake. It's just d. Let me fix this. Ky dt is equal to dy. Okay, I had recommended dividing just by y. That was my recommendation. This leaves us with k dt is equal to 1 over y dy. So all I did was this cross thing, I divided, and here I am. And now I can just integrate on both sides. I recommended leaving the k here. It's okay to bring the k on the other side, but I don't usually do that. Once I do this, I wind up getting kt plus c. The antiderivative of k is kt plus c. And then the other side, the antiderivative of 1 over y, is ln of y. No absolute value because population can't be negative, so I can avoid the extra burden of the plus minus part. Once I'm here, I remember that c just came about, so I have y of 0 is equal to p. Once I have that, I do k times 0 plus c is equal to the natural log of p. So c in turn comes out to be the natural log of p. At this point, I then can write kt plus the natural log of p is equal to the natural log of y. On the left side, I have kt plus ln of p is equal to the natural log of y. So I'll rewrite that. Kt plus the natural log of p equals the natural log of y. This point, maybe I'll write it in the opposite way. Ln of y is equal to kt plus ln of p. At this point, I'll exponentiate. I'll do e raised to both sides. So I can solve for y. Once I do that here, I get y equals, but it behooves me to factor this with the laws of exponents. E to the ln of p, e to the kt. Laws of exponents, in multiplication, you add the exponents to the same base, so I just reverse that process. Lo and behold, a magnificent result. E to the ln of p is p, and voila, we just derived from scratch the famous formula. Some of you may have learned it as F equals P e to the RT in high school. We have just derived exponential growth, and if K were negative, we just derived exponential decay for like radioactive decay. All those problems in high school are pre-calculus, where you did how long does it take your money to double, or your radioactive substance uranium to decay by 30%, which we're not going to do all those problems right now. But this is actually where it comes from. It's actually catastrophic that they give this to you in high school. They're just afraid you won't learn calculus and that you won't see enough real-life applications of math. So about 25 years ago, some genius decided, let's throw it in high school without any explanation whatsoever, just so that you could see it. But it ruined its beauty because people never know where it comes from. This formula doesn't exist unless you have integration and differential equations. That's where it comes from. Y equals P e to the RT and y equals P e to the KT. This is exponential growth and decay. Go ahead.
What if like your money grows at like x squared? Just like, would that still work? Like.
Well, the money, if you want your money to grow directly proportional to itself squared, then the equation will change. But generally speaking, your money grows directly proportional to itself, which is why we often use PERT for compounding interest continuously. Somebody asked me about the logistic model. We're not going to do that, but world population, they say, often does this instead. So world population is probably not this. They've done studies. It's probably not exponential, although in high school you may have used this for population growth. But if you're doing world population, chances are there's a point of inflection, meaning that you're growing quickly, and then at some point, it's probably happened already, the population is still growing, but it's not growing as quickly and is approaching a carrying capacity or horizontal asymptote. There is another differential equation that represents this. It's called the logistic differential equation. If you took BC Calc in high school, they do touch upon this. And then the algebra to solve the differential equation is much more intensive than what we just did. But this is an alternate differential equation where the slope would wind up being pretty positive, and then it gets less and less positive. The differential equation that results is actually a separable differential equation, so it is something you could solve, but you need something called partial fractions to do the algebra, something we didn't really cover in this particular version of Calc 2. So what I'm happy with you knowing this guy right here. That makes me very happy if you know this guy right here. This is a pretty popular formula, and we were able to derive it literally from scratch. Any questions about this?
What do they represent again? What does K represent again? Like the rate of growth?
Yeah, K is called the rate. So it's often when you use K, it's often considered the continuous growth rate, like 3% per year compounded continuously or something like that. So it's your percentage rate. So like you turn 3% into 0.03, and that's like your K value. Okay.
Beaver?
Yeah.
Why did you make the Y like with
Modulus of?
Why did I make the y what?
I forgot the name of it.
The f?
No. Is it called modulus?
So the y is not called the. So we're not doing anything
No,
with.
no, not that. The sign it usually has like ln and then a sign with y. I forgot the name of the sign.
The absolute value?
Yeah.
Okay, thank you for clarifying. There's no absolute value because normally I would put ln of absolute value. So when I did the integration, it would be traditional when you integrate to do kt plus c equals ln of the absolute value of y. However, since population is already positive, I didn't have to deal with that in this real life problem. I could just eliminate the absolute value.
Okay, thank you.
Yeah, normally if it comes from just an abstract problem, you would need the absolute value like we had in an earlier example with dy dx is equal to y, because it wasn't necessarily stemming from a positive population per se. But in this particular real life example, we could get rid of the absolute value because people must be positive. All right, let's move on to, what number am I up to? Number 9 or 10?
10.
Okay, 10, perfect. So, here's a surprise. To end with this one, this will be enough for us for this topic. Okay, so here I have a differential equation. Dy dx is equal to negative x over y. So what's different about this last example? What's different about this?
There's two variables.
Right. So it's interesting. The slope, and this is Calc 3 actually, not Calc 4. The slope is actually slope is actually a function of two variables, which you'll learn about in the next calc course if you take it, f of x comma y. So in fact, the slope is going to be a function of two variables. So you have an x and a y, you plug them in, and that xy pair determines who the slope is. So this differential equation is actually a function of two variables. Nevertheless, it is still first order and separable. And this is when I log off and log back on again. So I'll be right back. Okay, I'm back. All right, so let's return to our question here. All right, so dy dx is equal to negative x over y. So I really just wanted you, and then we'll see here, solve for the general solution. There's no initial condition here, but I'm bringing this up for a couple of reasons. This time the slope is a function of two variables, and I'm looking for the general solution. So go ahead, start the process, which you probably did already because we had to log off. So let me do it with you. If we cross, it's y dy equals negative x dx, and already it's separated, which is kind of nice. So already we have negative x dx, so things are looking good for us. And then I'm going to integrate on both sides. So it's already separated, and then I integrate. So when I integrate here, I get y squared over 2 equals negative x squared over 2, and I put the plus c on the side of the x. Now, there's no initial condition, so we're not finding the c. And while it's very easy algebraically to solve for y, I'm actually going to suggest not doing that because it will be anticlimactic. So while an explicit solution is possible, meaning you could solve for y as a function of x, that's what explicit means. Sometimes it's impossible to do that, and sometimes you just don't want to. This is an example of having an implicit solution being better than an explicit solution. Why? Because I think you'll see the solution better if it's left implicitly. So rather than solving for y, so I'm going to say implicit, do not solve for y, but maybe put it in some other form. If I just multiply everything by 2, if I multiply everything by 2, I think it's better. 2y squared is equal to, of course I'm doing it wrong, y squared is equal to negative x squared plus 2c. And rather than solving for y, I'll bring the x squared over because it reminds me of something else when I do this.
Was this the circle?
Yes, this is a unit circle. Actually, I shouldn't say that. It's not a unit circle. It is a family of concentric circles. I'll explain this. Center at the origin. Radius. Well, if you remember from high school, this is r squared. So the radius is equal to the square root of 2c. So that differential equation actually produces the general solution like this. It's a family of concentric circles.
Professor,
Yeah.
why is the y imaginary? Just like y alone? Because I did that.
So what do you mean the y? Tell me what you did.
I just saw for y and like it's the square root of negative x squared, so it's imaginary, right?
No, it's not imaginary. So if you solve, you get plus or minus the square root of negative x squared plus 2c. That's not imaginary. Because if x is, you can pick x values that are negative and positive and sometimes get a number inside here that is positive. Just because it is a negative underneath here, it's not a negative number, it's a negative variable. So there are certain cases that will make the radical positive. So this is not.
Okay.
Yeah. So this is a family of concentric circles, center at the origin, radius square root of 2c. But I can't resist showing you what's actually happening here. If you have dy dx is equal to negative x over y, the differential equation is actually forming, in some ways, the concentric circle. Hold on one second. So if you pick any point that you want, you can actually find the slope. So what's happening here is, and we have something that we call sometimes a slope field, sometimes it's called a vector field, and sometimes it's called a direction field, depending on the course. So let me explain what I mean by this. If you have dy dx equals a negative x over y, and I go to the plane, and I just pick some random points in the plane. I don't know, I'll pick a point here like, I don't know, 2, 3. So at 2, 3, at the point 2, 3, which is here, the slope would be negative 2 divided by 3. So at 2, 3, I'd put a little dash to show a negative slope, just a little dash. Then I could pick random other points too, like, I don't know, I could pick like negative 4, 7. So if I did negative 4, 7, negative 4, 7 is here. And if I plug negative 4, 7 in, I wind up getting positive 4, 7. So I get like a slope like this. Then I could pick random points like, I'll pick another one, like maybe like 0, I don't know, 0, 5. So 0, 5, then at the point 0, 5, I'd have a slope of 0, so I'd have like a horizontal. If I let the computer just draw dashes for slopes, positive like looking like this, 0 like this, negative like this. Suppose I have the point, I don't know, like 9, 0, then it would be 9 over 0, which would be like undefined. So if you let the computer draw all of these dashes for slope, positive, 0, negative, more positive, a little bit steeper, more negative, steeper, then what happens is, and this is the amazing part, if you let it do this for lots and lots of points, you'll kind of get like the ghost of the solution. You'll get all these dashes, lots of them, and if you play connect the dots with the dashes, you wind up getting the concentric circles, which are the solutions. Now you might say, why play such a silly game, B. Byrne? The reason is because some differential equations, in fact, most differential equations are not solvable algebraically or analytically, either because you can't separate or because you can't integrate. So then mathematicians and applied mathematicians are stuck, and they're like, how do I understand a differential equation if I can't solve it, especially if it's important in a real life scenario? You use computers to draw the graph of the differential equation in the exact same manner that I just alluded to right now. So often a differential equation can't be handled analytically, algebraically, and computers will have to at least draw the solution using many, many little dashes. So this is a numerical and graphical solution to help us understand the differential equation. So you might study something like this with a certain degree of intensity in Calculus 4.
Sir,
Could you? Oh, sorry. Go ahead.
how are the slopes related to the circumference? Just out of interest.
So basically the circumference, if you just draw the circles around, the circumference is just going to be getting greater. So that's actually a very interesting math question. So the slopes here obviously are going to adjust to be, I don't even know how to put it in words exactly. You can see as each circle's circumference is getting greater and greater. So what's happening is these dashes are just a little bit more dense over here for each of the smaller circles. Somebody else had a question.
Would there be a way to sort of relate this specific differential equation to like polar coordinates? Well, because this is rectangular, so I was just wondering, because when you graph the polar coordinates, it is on a circle. So that was my thought process.
Yeah, and I mean that's a good question. I mean, you can do some polar coordinate work with differential equations. You can always relate almost everything, but in this particular example, rather, the differential equation just happened to result in circles, which reminded you of polar coordinates. Most differential equations won't give circles per se. I just chose the one that gave circles on purpose just because it was interesting. So not so much here with polar coordinates. Anybody else here? This is just a prelude. The only thing I'm going to ask you on WebAssign this Thursday night and on the final is to be able to solve a differential equation and maybe some basic word problem where you have to set up a differential equation and solve it. And you'll see what I mean on WebAssign when I put forward the questions on Thursday. So we're talking about solving like we did tonight, and maybe like a little word problem where you have something directly proportional to something and you have to set up a differential equation and then solve it accordingly. And you'll see what I mean in the WebAssign perhaps. Questions here? All right, so we have only one more week of new material, which is next Tuesday. You're, of course, welcome to come Thursday if you just want to shoot me an email if you don't have the login for Thursday Zoom. But next Tuesday is our last new lecture on the topic of volume, which was in AB and BC calculus. So we'll be going back to section 6.2. I will give a historical perspective on volume next week. We'll be talking specifically about disks and washers, which I know some of you studied in the past. And then we'll go on Thanksgiving break. I'm not going to have class the Tuesday night before Thanksgiving, but we will definitely do a review the Tuesday after Thanksgiving in preparation for the December 9th final, which happens to be a Thursday night for both classes from 6:30 to 9:30 p.m. I changed the time for all of us. It is a 3-hour extravaganza on December 9th.
Professor?
Yes.
You just mentioned discs and washers, and I was like looking online and I saw some stuff about Calc 3 and saying that there's like a z-axis, and is that like related to discs and washers?
No, it's really not. So I won't. What I'm not going to do in this class, because it's not appropriate for Calculus 2, drawing pictures in on the three-dimensional system with the 3 axes z, y, and x. That's Calc 3. I will do some three-dimensional pictures next week, but they'll basically be projections from the plane. So we'll still be in 2 axes next week with 2 axes. In Calc 3, you would use 3 axes, but I'll leave that for that course for those of you taking it.
Are we going to do the similar thing where we have the same amount of questions for review as are on the final?
Yeah, I'm still thinking of the final, so I'm
Okay.
sure I'll do something like that. But the final is cumulative, and since I'm allowing it to count for the midterm, it's got to be substantially longer than the midterm. So I'm still thinking about the final, but I'll have a good idea in the next couple of weeks how many questions. So it'll definitely be longer. It'll definitely span back to some things we did prior to the midterm. And then, of course, there'll be a slight emphasis on the newer materials since the midterm.